Actually, it's not that long.
6.
Because this will end up being less than, oh, sorry, I did two things in my head at once, unfortunately.
1.0526.
Right, 0.526 units.
Newton meters per kilogram, or kilograms per newton meters.
And then a square root of that. What's the simple, what is, it's period, what is period? Therefore,
Second.
Second.
so 1.0526 seconds. So what we're gonna do now is, I'm hoping all of you have some sort of timing capability on your phones, more than just watching seconds go by, the fact that you have a stopwatch on your phones. We're gonna oscillate this thing, see how long it takes to go 10 times. And so we should get somewhere around 10.526 seconds for 10 oscillations. I will tell you right now, we will not. Because I'm gonna follow up with the question of why this does not work. And then we're going to account for that, make a new prediction with a different mass, and show that it does come out pretty darn close. But I do want the time for this.
Okay.
I guess you're gonna have to go by my count unless you can actually see it. I guess Selena potentially can see it, and John can see it, sort of.
Yeah.
Oh,
Yeah.
all right, Nick can sort of see it.
We're timing it?
Yeah, so I'm gonna take it down to a certain some amplitude. Notice that the amplitude doesn't show up anywhere in here. Take it down to a certain point, I'm gonna let go. I'll say 3, 2, 1, go. When I say go, I'm gonna let go, and then I'll count every time it does a cycle. So we're gonna do 10 cycles. Here we go, pull it down, and 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah, like 15 seconds.
15.21,
0.41.
0.41.
I have a question.
15.45.
No.
15.35.
I guess, Ronald, you were farther off from that?
No, man.
15.21.
It's a nice cluster in there.
Also
Because usually
did-
there's somebody who's got the
also did for
17.
Also did for every time it went down, every time you said 1.
Oh,
I don't know if you'd want that.
I don't need that
Stopwatch.
right now, but it's a nice capability to have the mapping feature.
Yeah.
Alright, so what is the average?
Um,
15 point something, but
15.3-ish, something like that. Maybe a little more.
Yeah, 15.
0.36.
so we got our prediction, 15.36.
No, 15.355, so yeah, for 15.3.
355, Nick, come on.
355.
Go around.
So that's for 10 oscillations, so we ended up with a period 1.5355 seconds. So the question is, how come we are off by 50%? And the reason of it's physics and physics doesn't work is not a real reason here.
Well, in this case, because it's not a closed system, that's the reason.
Well, it better not be a closed system because we do need the gravitational pull to pull it down. Or are you thinking of air resistance?
Yeah, air resistance.
Air resistance is not gonna count for 50% here. It's not going fast enough for air resistance to be of much importance.
Gravity isn't exactly 9.8.
Not the big issue, it is close to acceleration of gravity, 9.798 meters per second squared here. The reason I can do that as precisely is that when they started doing the gravimetric measurements, they actually, right out there, basically this height, the road, there's you got the traffic light over here, and then there's the next road over, and I can never remember the name of it, that tees into Silas Creek. Right in the median, right there, they did the measurement precisely for Winston-Salem. So we do have a more precise number, but 9.8 versus 9.798 is not significant, not gonna account for 50%.
It's not the harmonic, it's the dampened harmonic.
We did not let it go long enough for the dampened harmonic to cause the issue. And our spring constant, seems legitimate. I'm liking this much better than that almost 70 value that we almost put down. Well, what's left? If I'm feeling confident in the spring constant, I could be off my rocker, or there could be something else off.
Pi.
Wow, that would be a breakthrough. We'd be famous.
The celebration.
The mass,
What's wrong with the mass?
it may not,
Big.
it's not, uniform, I suppose.
That's not the issue.
Yeah. I'm just spitballing
Yeah, no,
But it's not directly centered.
not that big of an issue. We could
Slope.
offset that. I mean, I've seen people set up things where it's cross beamed and you hang the mass from the middle.
The slope.
It's generic enough that you probably could get away with that argument, but however, there's something more specific, physical about this, why that did not work, and we have to take it into account.
The material
Of,
of the spring.
keep going,
The elasticity.
wrong turn,
Of the weight.
The weight.
not weight here,
Mass.
mass of the spring. In simple harmonic motion, all the mass is concentrated at the end, but this, adding a bit of reality, this has mass in it. That 0.04 is only what I attached to it. This mass right here needs to be the mass of what I hang on to it plus the effective mass of the slinky.
So you need to count the mass of the slinky too.
The effective mass of the slinky. We're not gonna put the slinky onto a balance and find out what the mass is, but we do need to take it into account. And we have run out of time, and unfortunately, we're gonna leave it on, hey, it didn't work, but when we come back from spring break,
The spring break.
I guess we've got, the quiz is on Wednesday, so, yeah, Tuesday we'll be able to knock this one out. No problem. So we're not meeting next week. I hope you all have a safe week.
Ronald, we need to make sure our data is the same. For the winter.
So for the lag, does the graph seem to be the same